Yeah, I started now. Okay, so we have 3 types of motions. One, just the rigid body translation, then the rotation. The other one is that the shape is kind of squeezed. It's like a strain or a compression, as we have it in acoustics. So, but we will see some illustration of these 3 modes afterwards. The whole motion of the fluid particle can be described by the rate of the strain tensor, as we see it here. It has some part which describes the strain itself and some part that describes the vertical part. So the second one.
I have a question. Could
Yes.
I ask? Is the distortion of the shape is by the shape of our control volume omega meant, or what is meant by shape?
Just you have a control volume omega and you have some fluid particles in here. So the small rectangular is now a fluid particle.
Yeah.
And the distortion of a shape would look like you have, oh god. Oh my god, this is not really
okay, so
rectangular,
that is distorted now.
Yeah, that is distorted like this.
Okay, thanks.
Or probably like just this, getting a little bit slimmer, squeezing and stuff like that.
Okay, but the control volume stays constant.
Yes.
Okay.
So the density is enriched. So
yeah,
if you have this, then yeah, the density goes up or down.
Okay.
So that's more or less what is meant by them. The distortion of the shape. Okay, so you have then this rate of the strain tensor and the translational motion and potential flow is due to the boundary conditions. Okay. Any idea why it is like this? But we will see it later anyway. So potential flow arises due to the boundary conditions. This means if you have let's say a volume like this and we are approaching this volume with this u infinity, and we just think of it, okay, a block velocity profile is streaming through the domain, and there is no distortion in the domain itself, then the block enters and the block kind of flows out of the domain again. And this means that there is no vorticity generated inside, and there is also no strain or distortion happening in this domain, and therefore it is purely potential and is just due to the boundary conditions of the acting on the domain, on this now differently shaped domain. So that's kind of potential flow. If we do or have vorticity, or we would like to generate vorticity, we have to place an obstacle inside the domain. And we have to have a viscous fluid. Then we can generate with an obstacle vertical structures. There's another possibility to create vorticity, that you just add some vertical sources there. Yeah. And yeah, generating strain and stuff like this is also generated by obstacles at higher Mach numbers. And there is another kind of very prominent representation of this strain parts if you have a nozzle and the velocity is above Mach 1, then you have here some shocks there. And these shocks are usually kind of representatives of this compression mode or expansion mode. So 3 modes: potential flow, vorticity, and some compression. The vorticity itself is now computed as the curl of the velocity of the field. I think all of you already know it because you did the computations of the exercises. So very simple formula. I think it was calculation exercise 4 or something like this. Usually just the formula would have been enough for that. And the fluid, now this vorticity also related to an angular velocity, and how the relation is for a typical velocity setup here. That we have a fluid which is moving with an angular velocity of capital omega, then the vorticity is twice the angular velocity of this velocity field described by that shape. This is just an illustration. It's more or less not really important for you, and it will not happen in real world. So just take the message that the vorticity is somehow related to an angular velocity. That's important. The rest of the example is just to illustrate it. Okay, any questions on that? Okay, then we move on with the next slide. Vorticity is, so just you have more or less it forms closed loops, so like the magnetic field, it forms somehow closed loops. It can also be described in a similar setting. So for instance, if you consider an incompressible flow, this incompressible flow looks very similar as the magnetic field itself, and it also can be described by a vector potential. And this is how the two fields are somehow related. And it's just interesting to know, and that all the field lines are closed, and you can form some vortex tubes. And for instance, as we had it here, I'm jumping to the first slide. Oops. Here in the graph of the fan, here you find some kind of these vortex tubes here, and this is just an illustration of what this is. So that is how we can use it during the flow visualization, and to identify structures where acoustical sources are probably located and where acoustics is generated. Okay, so we have vortex tubes, and there is a reformulation of the momentum equation or momentum conservation we had learned before. that we can reformulate the conservation of momentum in terms of the vorticity, and that the vorticity is somehow conserved and how it is dissipated and how it is transformed. Having this type of momentum conservation, which is also called a Crocus form, then it is related somehow to acoustics with the total enthalpy in a homoentropic flow. And the total enthalpy is described like this. And here we have the lambda vector, which is at low Mach numbers, a very localized sound source, and it's computed by this, that the vorticity times, so with the cross product of the velocity is the lambda vector, and this is a typical sound source in low Mach number applications. And usually aeroacoustic analogies using lambda vector as a source term are called in the category which is called vortex sound. Yep. So we have the vortex sound analogies, and this is more or less a bunch of methods that are specialized for different flow configurations and are used in low Mach number applications. Any questions on that? Okay, then we proceed. Yes.
So does it mean if the lambda vector has large numbers or large numbers, is the vortex sound louder if there
Yes.
are large numbers? Okay.
Yep. So there is a direct relation between if the magnitude of the lambda vector typically increases, then you have more sound due to the vortices.
Okay, thank you.
Yeah, that's the first message of the story. You will then learn in the third or in the aeroacoustics chapter that you also have cancellation effects of the different sources and stuff like this, and that you have some compensation, and you can use kind of active noise control to kind of mitigate some sources. But yeah, typically there is the relation. If the lambda vector increases, then also the sound that is propagated increases.
And where does the lambda vector point to? Is it the direction of the strongest beam of the sound source, or what is it?
So probably then we have to jump to the wave equation. So vortex sound. Here we find the lambda vector. And the sound source is the divergence of the lambda vector. That means we have the kind of a spatial, the lambda vector is pointing in one direction. And as it changes over the space and its divergence, so its flux through a control volume is essential. So it's not, if the lambda vector is more or less constant all over the domain, then it will not happen something. So first of all, because the wave equation doesn't propagate it, and the second thing is that we have no spatial variation. It's also important that we have a spatial variation.
Okay. Okay, thank you.
Okay. Okay, yeah. So we have the lambda vector. It is pointing in one direction. I think when the velocity is like this, with the velocity here, then you have kind of this right hand rule. Then the lambda vector is somehow pointing in. Yeah. If I manage it, then it's somehow pointed in this direction. So yeah, this right hand rule of kind of vector representation. So that's more or less the direction of the lambda vector. And then we, for the sound source itself, we have to compute the divergence of the lambda vector. So how the spatial shape is changing as a flux through the control volume, more or less. Okay. This would mean that just forget up there that we have here the vorticity, so the divergence of would have here the lambda vector. Then we can also describe that the lambda vector, which is going through the surface of the control volume, is essential for the sound sources. Okay, perfect. Then we go on with the next slide. So having this crocus form of the momentum conservation, we can kind of develop a vorticity equation. The vorticity equation is here, and we have two terms. Okay. We have two terms. The first term is how I just read out the definitions there because it's more or less being precise on that. In the absence of a viscosity, so viscosity is here. So the first term is this. The vortex tubes are rotated and stretched in a manner determined by the flow itself. So if you have a flow, then the vortex tubes itself are already stretched and kind of elongated, and the cross section is reduced, so it's somehow conserved. And if it happens like this, that the cross section is decreased, then the amplitude of the vorticity has to increase in order to preserve the strength of this vortex tube. So yeah, that says the first term, and the second term says how vortical structures are generated and diffused through the flow by the vorticity. So this means if you have a wall, having some wall here some flow, then you usually have a boundary layer there, and this equation says how the vorticity which is present in the boundary layer is diffused into the domain. So how vortical structures are kind of translated through the boundary layer. yeah, that is the idea of the second term in this momentum conservation equation. Any questions on that? Yeah, anyway, it's just for you for an additional understanding. It's not very important for the understanding on the aeroacoustics analogies. Okay. Then some other ideas about the vorticity. If we have an incompressible flow, so incompressible flow means at low Mach number that we have no acoustics in the flow itself, and we have an incompressible flow without vorticity, we can describe the whole velocity field by the potential flow. This means that you're just solving this equation for the potential flow, and that's it. It's a simple Laplace problem, and you're finished. Potential flow is somehow easy. It's also linear, and there's nothing happening. For an incompressible flow with vorticity, we have this Helmholtz decomposition in an unbounded domain. It can be purely described, or it is purely described by a vector potential. So all vorticity which is generated in the domain or is in the domain must be also generated somehow. This means, let's imagine you have here some infinite space. The infinite space looks like this. If vorticity is happening here, it has to be compensated by another mechanism somewhere there. Yeah, that's more or less how this is, how the idea of the flow is. So if you would like to have some flow somewhere in your room, you have to generate it. Yeah, and that's more or less the point of the incompressible flow in unbounded domains. But if you have a bounded domain, let's say we just cut out here a subdomain, then the whole incompressible flow is described by a vertical part plus a potential part here. So the potential part is due to the boundary conditions. If you have an unbounded domain, there are more or less just boundaries at infinity, and the boundaries at infinity you cannot influence and there is nothing happening. But if you now say, okay, you cut out the control volume, as we did it by this rectangular shape here, we are in a finite section and we have to deal with the boundaries, and there the boundary stuff is coming in, that we have here some term related to the potential flow and the other term is related to the vertical flow. And that's how the Helmholtz decomposition is acting on a bounded domain, that we always have to keep in mind, that there are boundaries and there can be flow exposed from the outer onto the domain itself. Okay, was this clear for everyone? Okay, perfect. Then I draw here a red line on the slide. this up there was interesting, and now we get to one of the core message of fluid dynamics, which is down there. So this is very important, and if you don't get it, just ask again. Okay, we have starting from this equation up there, and in infinite space we can use, or imagine we have an infinite space, it must not be infinite, but compared to the vortex distribution, it's just infinite. Which means, just consider with kind of this potato, and the vortex distribution is that small, then probably the domain is what this length here is much larger than the length here, so L is smaller than that. Then we can use a vector identity and derive this equation as an approximate on convex domains, and we use Green's function. I heard that you already don't know, or you don't know what's a Green's function. Is this correct? Or do you know what's a Green's function?
We heard it in different contexts.
Okay.
But it would be good to have a recap, I guess.
Okay. Good. So the first thing was we have this domain stuff here and the Green's function. I'll probably explain here. So if you have a differential equation, and let's say we have here the kind of any differential operator, then there exists a Green's function. We just call it G. There exists a Green's function. When we apply the operator to this Green's function, then then we have the identity on the right hand side. This means the Green's function is the inverse of the operator. So just having it in algebraic, if the operator would be matrix A and the Green's function would be matrix A to the power of -1, then we obtain the identity. And that's the idea of the Green's function. That is just the inverse of the operator of the PDE regarding all the boundary conditions and stuff like this. I have to get some electricity for my notebook. I will be here in a minute. Okay. So the Green's function is more or less the inverse of the operator. Okay, and if you have now an equation like we had it before with the potential and the vorticity, then you get the solution, but just now means a little bit complicated. You just integrate over the Green's function and the sources. I think you know it from the wave equation. Yeah, but that's how it works. So you obtain the solution, but just by integrating it. And that's it. Anyone knows why we come up with that? So just a pragmatic proof of this formula here down there. If you now, we have this equation up there. If you now multiply the Green's function in front there and also multiply it there, so I have nearly no space on that side, and then you integrate over it. And also do the integral over there. Then you have here with the integral identity of the, you have then here the delta property, and the integral of delta psi is purely psi. So that's it. And so this is how we come up with the equation down there. So I guess Green's function is more or less now clear. It's just the inverse of a PD. Okay. Then we come again to the essentials. Yeah, we'll wait. I will wait a minute that you can take your notes. Okay, good. Then we come to the essential of the fluid dynamics part. So if we have this equation and we know the Green's function, we can estimate how an incompressible flow disturbance vanishes with respect to the distance. This means, go there, as we go away of this disturbance and we look at it, then we see that the disturbance decreases with the 1 divided by the power of 3. So it's a rapid decrease of what we see from the flow disturbance. This also means probably go again there. Flow is minus x, or x to the power of minus 3. That's how flow decreases, and acoustics decreases by x to the power of minus 1. And comparable, now we see that flow disturbances are very localized around the obstacle, And acoustics is traveling much far into the domain, because acoustics in 3D decreases with x to the power of -1. And this, now we get an impression if the acoustics travels to our, yeah, let's say eye or ear. So to our head, then we experience acoustics even if we don't feel the sources. And that's more or less one of the key messages of this course. Good. Any questions on that?
So when you say we feel the sources, you mean like some kind of flow or like wind that does not travel to my to my head, but the sound itself does travel.
Yes.
Okay.
For instance, just think about it. You're sitting in a car. You open all the windows and you're sitting in front, or you are the driver. You probably do not feel much of the turbulences from the side mirror or even from the open window. But you hear a lot of noise. And that's just an illustrative example of how it is happening. Okay. Did this answer your?
Yes, thank you.
Okay. Perfect. Any questions on vorticity and acoustics, Green's function?
Is Green's function a singularity when you are at its origin?
It's very specific for different PDEs. So I'm not 100% sure.
Okay. Because I'm just looking at this at the lecture notes here, and I wonder what happens if we place our eye at the point of the Green's function.
Yeah, could be that it is singular.
Okay.
But usually there are some theorems in calculus, even if you have a singular function, there is a possibility to get the integral bounded. I think you all know from, I think it's the math course 1, that if you integrate, I think 1 divided by x from 0 to 1, it's, yeah, I think it's already bounded as the power kind of is higher than a third. Yeah. So if you kind of integrate 1 to the 1 divided by the power of n, if n is large enough, then the integral is bounded. And that's more or less how this whole theory also works. Okay. Any other questions?
I don't know. if you are familiar with these terms, but in basic acoustic lectures, we have subdivided the sound field into like a near field and a far field, where
Yes.
the near field was in close vicinity to a vibrating object, and the far field, it's far away from the
Yes.
sound source.
Yes.
Can this be applied to these vortex sound sources as well?
Yeah. Usually it can be applied. I don't know for sure if you get any benefit from it. In acoustics, I know you get a benefit from it, and we will partly cover it in the acoustics part.
Okay.
Yeah.
So are the vortices and the vortex sound sources rather a near field phenomenon or a far field phenomenon?
They are a near field. So the vortex sound sources, how they translate into acoustics.
Mm-hmm.
They are a far field phenomena, as we had it there. Yeah, we see it then there. So Paul did here some simplifications on the sources, and he found that the lambda vector is the leading term for the far field. And this one is important in the near field. That was his conclusion.
Okay.
Yes. Perfect. Okay.
Thank you.
Good. Then we will proceed with the kind of last topic towards acoustics. Sorry. We have conservation of mass. Probably I just let you do your notes, and then we go on with the topic towards acoustics. Okay, then we start with towards acoustics. So just to get an overall impression, fluid dynamics is the global area or field of mechanisms, and acoustics is, yeah, acousticians don't like to hear it, but acoustics is more or less a branch of fluid dynamics. So it's a specialized topic, but nevertheless in its rich field, it's also a very large discipline. Doesn't mean that we are exclusively the one is better than the other. So for low Mach numbers, and we have conservation of mass, we can rewrite the conservation of mass in this representation, and we can do also apply Helmholtz decomposition on the velocity field. And if we apply or insert this into the conservation of mass, we detect that the changes or the variations in the density along a streamline are connected to a compressible part, and that the vertical part, so all the vorticity, is 0. This means density variations are connected to compressible phenomena. And this compressible phenomenon is, for low Mach number, purely acoustics. So this means all density variations in a very low Mach number flow are acoustical variations. Any questions on that? Okay, to sum up, density variations at low Mach number are connected to acoustics, and these density variations propagate, and we can hear it as sound. So these density variations are acoustic modes that propagate. Yeah, and you see how these modes are connected to the compressible part of the Helmholtz decomposition, and how all forms together a very interesting theory itself, and has very explanative character. Okay. Maybe some additional background on Helmholtz decomposition. So if you're doing a Helmholtz decomposition in infinite space means that we have just two parts, a vertical part and a compressible part. At low Mach number, this compressible part is acoustics. At low Mach number, the vertical part is the incompressible flow. If we now do it on a interesting word, manifold, which means that we have some whatever shape of the domain, we get a third part, which is the potential flow. So the vertical component is this. So we have kind of a rotation. The expansion mode is the compressible stuff, and the potential flow part is represented like this, and we have here some irrotational deformation without any volume change. So doing Helmholtz decomposition on a bounded domain, we have three components, and that's more or less it. And important to note, if we have low Mach number, the density variations are connected to acoustics, and these are the acoustic modes that propagate. Okay, any questions on that? Okay, and the three parts here of the Helmholtz, on the manifold, it's called Helmholtz-Hodge decomposition, are then computed by these three equations. The one for the potential flow, it's just the Laplace equation. Then a curl equation for the vertical field. I said before, this is more or less connected to the magnetic field. In the magnetic field, you have a similar equation which looks like, yeah, the curl of, I think must be the relativity x. No, this is not here. The curl of the relativity times the curl of the magnetic potential is equal to the current density. So this is how they are related. Yeah, must be like this. Yeah, somehow. And the last mode, so the compressible or radiating acoustic field, can be obtained by this Poisson equation. This is just post-processing of a CFD solution. This means if you do this, the acoustics must be already present in the velocity to get the acoustics. So this is just a recalculation of a field or a post-processing. And this is how you can compute the individual parts of the decomposition. Any questions on that? Anyway, it's not so important for the aeroacoustic analogies. Just keep it in mind if you have to do a Helmholtz decomposition at some point in your future life, then you can go here and use the formulas there. The whole stuff towards acoustic is presented here in this publication we did last year. Yeah, there you can just look up some details on that and how it relates. Probably you just follow the web link and you will find also some graphics on how acoustics looks like and stuff like that. So if you're interested, just go to the web link there and you will find some further information. Okay, any questions?
So we arrived at this point by using Green's formula.
At which point?
You used Green's function to solve the Laplace equation for the vector potential, I think.
Okay, this here.
Yeah.
Yep.
And does these results that you presented just now in any way depend on the Green's function? Because I mean, probably you could use some other function to solve the PDE.
Yes.
Or
the Green's function was just used to get a free field estimate.
Okay.
Therefore, I said before that the length of the vorticity distribution must be small compared to the length of the domain.
Okay. So
This was the assumption that we can use a free field Green's function.
Okay. So the solutions that you presented now do not depend on the Green's function. I mean,
yeah, regarding the assumptions, they do not depend on the Green's function.
okay.
But in general, they will depend on the Green's function. But the 1 divided by the x to the power 3 is just a rough estimate on how flow disturbances will decrease compared to an acoustic model regarding a similar Green's function.
Okay. So my assumption is now that you will present a solution for the 3 terms, for the 3 flow terms: vortical flow, compressible flow, and potential flow.
Yes.
Okay.
So you can't just execute it. I don't do it in the lecture.
Okay.
You can just execute it. And we usually solve using we solve the 3 equations by using finite elements.
Okay, thank you.
So a finite element is just a different method. So on the one hand, you have Green's functions. It's more or less a more analytical way. Then you have finite differences, finite volumes, finite elements, some spectral methods, wavelets, blah, blah, blah. There are a bunch of methods you can use. And all methods are, yeah, the same good for solving stuff like that.
Okay, thank you.
And yeah, for any details how we did it for a real velocity field, you can find it here in this, yeah, recent, or one of the latest publications we did on that. But it's just for you to get some additional background if you would like to. It's not mandatory, and we will not cover it in any way during examination of stuff like that. Yeah. Any other questions? Okay. Perfect. Then should we do a 10 minutes break and then go to the exercises? Okay. Perfect.